Hello, this is IT Taro. This time, I would like to investigate the Illuminance sensor. I would like to understand the basic specifications of the Illuminance sensor and do electronic work. I tried to see if it can be used for lux measurement. Since the data sheet is the most accurate data for sensor performance, this time it will be how to use and measurement results when using with ESP32. I would appreciate it if you could confirm it as one practical example. Let's check what we're talking about this time. First, I made a list of sensor usage posted on this channel. It introduces the model numbers and electric circuits used in all sensors, and how to use electronic work. We have research sensors that can be purchased in Japan and are introducing the cheapest sensors that have been confirmed to work properly. This time, it will be a post about the Illuminance sensor. Move on. Here is the table of contents for this time. First, check the mechanism of the Illuminance sensor and the list of sensors. Next, check the specifications of the ESP32 and each sensor, create a circuit and program, and measure. Since it was necessary to review the measurement result once, change it and check the measurement result again. Finally, it is a summary. Move on. I will briefly check the mechanism of the Illuminance sensor. Regarding the mechanism of the photodiode, it seems that the substance absorbs photons by interacting with light and emits it as electrical energy. In other words, it uses the mechanism that electricity flows when light is given. It seems that LEDs can generate electricity as well. I added a detailed mechanism on the right side, so if you are interested in it, please refer to it. I will omit the explanation. Move on. The sensor used is a phototransistor. A transistor can be used as an amplifier because a large current flows between the collector and the emitter when a small current flows through the base. A phototransistor is a product that combines a photodiode and a transistor, and the small current generated by the photodiode can be amplified by the transistor and extracted. A photo IC diode is designed so that it can be handled by amplifying the current with an IC instead of a transistor. Both products are photodiodes with amplification functions added. Move on. Let's check the lux, which is a measure of brightness. I think it will be about 10,000 to 100,000 lux for sunlight, and about 100 to 1,000 for indoor lighting. Finally, it seems to be about 10 to 100 in a dark place in the room. I would like to try to see if these lux measurements are possible. Move on. This time, it will be a list of sensors to be investigated. It's cheaper to use an overseas mail order site, but I don't use it because there are imitations even with the same model number. We research and select reliable sites and shops of Japanese and overseas manufacturers. Products that support 3.3 volts and 5 volts are selected in order from the cheapest of the same type. However, CDS cells are excluded. Cadmium seems to be a regulated element in Europe. We think that we should avoid using items that have a large environmental impact, so we excluded them from the selection. Move on. I tried to classify the sensors to be investigated. I think they can be classified into 3 types: phototransistors, photo IC diodes, and modularized products. I think that all of them will be products that use the mechanism of the photodiode. Therefore, illuminance can be measured by current. However, modularized products are likely to have built-in resistors, so the specification is to measure the illuminance by changing the voltage. Move on. Regarding the ESP32, this time we will use the ADC terminal to measure the voltage. Regarding the ADC terminal, ESP32 has 2 ADC circuits. The ADC circuit is an abbreviation for analog to digital converter, and it is a circuit that can acquire analog voltage values. Since the obtained value and voltage have a linear relationship, for example, if a value of 1000 can be obtained, it can be converted to about 0.8 volts. In addition, the ADC circuit has an 11 decibels attenuator inserted as standard, making it possible to measure from 0 to 3.3 volts. If the attenuator is not inserted, it is possible to measure from 0 to 1 volt. Just to be sure, I set the attenuator to 0 decibels in the program, and it certainly measured from 0 to 1 volt. Since the standard resolution is 12 bits, it is possible to acquire values from 0 to 4095. If this value is set to 10-bit, it will be possible to obtain numbers from 0 to 1023. This time, we will use the standard values for the attenuator and resolution due to the measurement range. As a point of caution, I think that the limitation that the second ADC circuit cannot be used with Wi-Fi has not been improved yet. Since 2 ADC circuits are used this time, the network cannot be used, and the data is acquired by displaying the data on the serial monitor. Move on. Check the precautions of ESP32. The maximum input voltage that can be handled is 3.9 volts. There are other important specifications, so please refer to them. Since we are only using the ADC circuit this time, we will only use the maximum voltage with caution. Move on. Let's check the specifications of each sensor. If you check the datasheet, the basic specifications of F3 and F5 will be the same, so we will check them together. The difference comes down to the angle at which you can get the light. There was a relational diagram between flowing current and illuminance. There is a graph only for use at 5 volts. Since the current changes depending on the brightness of the light, we will measure the illuminance using that characteristic. Also, as a circuit example, it seems that the current is grasped by measuring the voltage using a resistor. It seems that the maximum current flows is about 10 milliamperes, so I would like to pay attention to that point when deciding the resistance. Move on. Since it is difficult to directly measure the flowing current, the current is calculated by measuring the voltage applied to the resistor. If you know the voltage and resistance values, you can calculate the current using Ohm's law. The ADC circuit can measure up to about 3 volts, so 10 milliamperes max is 300 ohms. Also, current flows through the ESP32's ADC circuit itself, so I checked whether accurate measurements were possible. According to the site I referred to, the resistance of the ADC is about 15 mega ohms, so it's about 1/10,000th or less, and I judged that there was no problem with the error level even if I ignored it. Move on. Calculate the relational expression from the graph of the flowing current and lux. We will use this formula for lux measurement. The relationship graph is calculated assuming that both axes are logarithmic graphs and that the relationship is represented by a perfect straight line. The linear relationship of the double logarithmic graph can derive the slope and intercept as shown in this figure. To calculate the slope, we obtain two values from the graph by a measurement. It can be obtained by applying the obtained value to the formula and applying log to both sides and transforming it. The intercept is 10 to the power of 0, that is, the value at 1 is obtained and applied to the relational expression. As a result of calculation, the conversion formula from current to lux is shown in the lower right. Although it is a visual estimate, I checked the values at several points on the graph, and I think that there are no major problems because generally good values are obtained. We will program this conversion formula to obtain lux. Move on. It becomes NJL7502. This can also be used in the same way as the previous sensor, and although the numerical values are different, the content is exactly the same, so the explanation is omitted. Move on. It becomes S13948. Although it is a photo IC diode, it can be used in the same way as the previous sensor. The data sheet recommends connecting a capacitor as a low-pass filter to eliminate high-frequency noise, so I used it. Move on. It becomes a sensor of growth. It may be somewhere, but I couldn't find the schematic. As a usage method, it seems that the voltage is measured at the ADC terminal and the brightness is obtained. From the outside, it looks like a resistor and an amplifier are connected to the board, so it seems that the circuit is like that and has the same configuration as other sensors. It seems that the resistance is wired, but I did not know the resistance value used. It is not possible to change this resistance, so we will use it as it is and see if it can be used. Move on. I will check the circuit. Supply 5 volts power to each sensor and measure the voltage by connecting resistors in parallel. Therefore, it is connected to the ADC terminal. ESP32 has 2 ADC circuits, so we will measure 2 sensors at a time. Move on. This is also the same as before. Use the S13948 by wiring the capacitor as recommended in the datasheet. Move on. It becomes a sensor of growth. The resistor seems to be built in, so I connect it to an ADC and measure the voltage. Move on. Be a program. Measure 2 sensors with this program. First, set the ADC port in the setup function. Voltage is measured every 5 seconds in the loop function. First, I'm measuring voltage with an ADC. I am getting 2 values. One is the value from ADC 0 to 4095 and I need to convert it to voltage. The other is a function that can directly obtain the voltage value, so I also use it. I am getting 2 values, but I am using the voltage value calculated by the function. Then calculate the current according to Ohm's law. Using the relational expression derived from the graph earlier, lux is calculated from the current. Finally, the obtained value and the calculated value are output to the serial monitor. This measurement is performed for 2 sensors every 5 seconds. The same program is used for other sensors, so the explanation is omitted. Move on. Use a smartphone app as a lux meter. I use 2 smartphones and use the average value as lux. Move on. Here are the measurement results. The growth sensor cannot be converted to lux, so the voltage on the right axis is displayed. As a result, it is possible to grasp the brightness, but it is difficult to use it for grasping the lux. It means that it is difficult in the usage example using ESP32 like this time. In addition to the Grove sensor, it is also difficult to determine whether the indoor lighting is on or off. It can be used when the brightness is extremely different, such as daytime and nighttime, but the difference in fine values can only be used when used in a fairly bright place such as sunlight and shade. Also, it is difficult for the Grove sensor to accurately measure above 5000 lux, so I think it will be a product that focuses on brightness for indoor use. This is the result I got with the resistance value this time. Move on. As you can see from the graph, the relationship between current and illuminance is logarithmic, so for example, 0.1 mA, which is 1/100th of 10 mA, cannot be measured at the same time. It may be possible if you use a fairly accurate measuring instrument, but if you use it with ESP32, it means that you can only grasp a certain area. At 300 ohms, it will specialize in a fairly bright place. When using it, it seems necessary to focus on the brightness of some place and use a resistor. Therefore, I decided to measure the 10k ohms and 200k ohms resistors as shown here. Move on. If the resistance is increased, the voltage will increase even if the current is the same, so I checked whether there would be any problems with the input voltage. If we increase the resistance of all sensors, the voltage will exceed 3.9 volts in sunlight, so we changed the input voltage from 5 volts to 3.3 volts. Due to this voltage change, the conversion formula used in the lux measurement was a graph at 5 volts, so it can no longer be used. Move on. 5 volts may exceed the allowable voltage, so it is not desirable, but as a reference, I measured it with 10k ohms to see if I could measure the lux. The results were again unusable for lux measurements. Since the lux values differed by orders of magnitude, the configuration using the ESP32 was unusable for lux measurements. Move on. This is the result when the supply voltage is 3.3 volts and 10k ohms is used. It is possible to judge whether the lighting in the room is on or off. However, I think that it is desirable to use it in a slightly bright room. It was difficult to measure in dark areas. Move on. This is the result when the supply voltage is 3.3 volts and 200k ohms is used. It is also possible to determine whether the lighting in the room is on or off. I think this is good if you want to judge dark lighting. If you install it in the corner of the room, etc., you will need to judge the darkness. In addition, it will be able to respond to even a little brightness, such as sunrise. Any resistor value will work just fine for an appreciable change in brightness. How much brightness you want to know in detail depends on the application, so it seems that you will have to select the resistance value and use it. Move on. Finally, it will be a summary. Regarding the sensor investigated this time, lux measurement is not available in the configuration using ESP32. If you want to measure lux, you need another method. However, all sensors can be used to reflect brightness. I don't think there is a big difference in terms of performance. For personal use, NJL7302LF3 seemed to be good considering the price and ease of use. But again, it doesn't matter which sensor you choose. Rather, I thought that it would be important to select and use the resistance value according to the brightness that you want to grasp in detail. This concludes the investigation results of the Illuminance sensor.